network with one hidden layer, one output layer using PyTorch. The hidden layer will be using the activation function Relu, and the output layer will be just linear. Okay, so first we'll import torch, and then we'll define the data type of our input and output. So torch float is basically float 30.
Can you make the font larger? Yeah.
So much. This will do?
Yeah.
Okay. And we'll define where we are going to run our code. That will be dot device, and we specify CPU here. So if we want to run on GPU, we'll specify GPU. So for the moment, we'll just run it on CPU. Now we'll define our input parameters. Let's say n is the number of inputs, and dimension of input, the number of features, the number of nodes in the hidden layer, and then our output dimension. So let's define it as, say, 100 inputs, or we have 100 inputs, and then say 1,100 features, and then so we have 100 hidden layer nodes, and then output, say we have just 10 nodes. So now let's initialize the input parameters. Let's say x is our input. So define torch dot randomly generated numbers, and then specify the number of inputs, and then the size, the input feature size, and then we want the input to be created on which device. So it's basically CPU, and we've already defined that. So we'll just use that as device, and then we specify the data type of our input. So we already defined that as E type. So we'll use that. And then we also randomly generate the matching output with the input. And just replace the dimensions. So it will be in and then E out. Now define our weight parameters. So we have two layers, one hidden layer and one output layer. So for hidden layer we have, say, weight parameters. We just initialize it to. And similarly, this will be input dimension, and the number of nodes we have in the hidden layer, and then same where we are creating this, and then the type of the.
So we copy and paste it.
Okay. Device, device. Similarly, we'll initialize the weight parameters for the output layer. layer, and then the
What is Y over here?
Y is the matching output against the input.
No output.
Basically, the actual label. So
The
each,
label?
each input, yeah.
So
It
X is the number, right?
Yeah, X is the input. It's just random numbers.
And Y is
The
Corresponding output.
number,
Y is also
float number.
float number.
Okay.
But isn't this an array? Can you
It is output like 10 numbers basically for each of the output layers nodes.
Okay.
So we can make it one number also. Like it's just an example. Then we have device, and then type also specified same. So now we have all the parameters ready. We just need to define another parameter, the learning rate. Let's put a small number, say 0.001. So now we'll start the training for range, say 1,000 times. And then we'll calculate the output from the hidden layer. So it will be the input is X, and then we do a matrix multiplication with the weight parameters of the hidden layer, and then we on the same line we can apply the activation function. They don't have a separate function. I think TensorFlow has a Relu function, I guess. TensorFlow has. Yeah, so they don't have a separate function as Relu. They use a function called clamp. So clamp has many other functionalities, but if we just pass parameters minimum equals to 0, then it would behave like Relu. So the meaning of this is anything less than 0 will be set to 0, and rest of the things will be set as it is, just like the Relu function does. And then from this we'll predict the output. So it will be the output from the hidden layer and matrix multiplication with the weight parameters of the output layer. And the output layer activation function is linear, so just the multiplication will give the output that we want from the layer. So from this we'll calculate the loss. So the loss can be calculated. Let's use a mean square error. So that will be you have the Y prediction minus the true value, true output value, and then we power it up to 2, and then we sum it up, and then we divide it by total number of the input and the output layer size, which is D out. and let's print the loss. This loss is again like just like TensorFlow. PyTorch also is based on the concept of tensors. So everything is a tensor here. So the loss that we calculated here, the variable, that is also tensor variable. To access the value of that tensor, we need to call a function on that, which is basically item. So it will return the value of that tensor, is basically one particular value. And then to oh, I missed one part here. When you are defining these weights, we also want the gradients to be automatically calculated for us. So to do that, we can just specify that the parameter here to this function. We'll say require gradient equals to true. And same thing also we want for W2. So we'll say so now
The required grad is already defined. Is that a function?
it's one of the parameters of that function. So when if you say require gradient equals to true for a particular tensor, then it will automatically, when the computation happens, it will pass back the data so that it will be able to compute the gradient automatically. So to compute the gradient automatically, there is a function provided which is called backward. So once we call this function, so whichever tensor have required gradient equals true, for those tensors the gradient will be calculated. Now we need to update our weights based on based on the calculation from here. We have to use this function because PyTorch has a autograd module which calculates automatically gradients. It keeps the history of that. So it works on almost all the tensors. But if you want only a particular tensor to have the gradient, then you have to call this function.
Excuse me, what is the low stat item?
Which one, Professor?
Low stat item function. Low stat item function.
This will return the value of that tensor.
Value of the tensor.
Yeah.
Okay.
And
What is the no grad?
this is a wrapper function. They say if when you are building up the computation graph dynamically, there is something called autograd in PyTorch.
Mm-hmm.
It keeps the history of everything, the computation, and computes the gradient. But if you only want gradient of only few of the nodes,
Mm-hmm.
so you have to use this. Otherwise, it won't work. It throws up some errors.
So, okay, continue. Mm-hmm.
So it's a learning rate. The gradient is stored in a particular variable, which will be w1 dot gradient. Similarly, we'll do for So once we have utilized the gradient for a one particular loop, for the next time to use the gradient, we need to reset it. So we'll reset that to dot gradient and we'll make it to 0. So this will reset the gradient of W1 and then this will also.
Why there is a underbar behind the zero function?
That's the way the function is defined.
So is there any meaning with the underbar?
I'm not sure.
So write it down and prepare answer
Sure.
and update your answers in the selection.
Okay.
Yeah.
Sure.
Did you write it down?
Yeah, I'll let it down in notes.
Oh, please don't use the note pen.
Oh.
Use pen and paper. Yeah.
Okay.
Here's
Oh yeah.
so there is a reason for it.
Does this work?
I'm not sure.
Oh no.
Same. What was your question? What did you say?
So there is a reason for this one?
Are you asking me?
Yeah.
No, I don't know. Yeah, that is my question.
So then the loop will start again and the same process will be repeated for the total number of efforts that will be defined.
So what if we don't add we torch the Nograd line? So what will happen?
It says it gives one error message. We'll do that. Like we can run it and then.
But can you give me a meaning? So why we need those Nograd and what will happen if we do not put those messages? Can you explain it?
Yeah, it's basically like. I have not gone through the details of the autograd. It's not visible in this one.
Without that, not from.
Oh,
Not on this screen. I can zoom
we
in
get the
if you wanted
inputs.
to capture
Suppose you're just considering, say, 2 nodes, and then this is the output. So this is input, this is, and then here we get this y. The inputs, the hidden layer, the hidden layer, so that's all. So it builds up basically this graph, like when you define all this. So the flow will be like this. So this one W1 and this W2, these the weight parameter tensors, they are the leaf nodes because there is nothing connected to this. They are just input to the graph. So I'm not sure how the autograd works. What I read in the documentation is when this autograd is being used for automatically calculating the gradients, then it takes the whole graph and calculates based on the history, it calculates the gradients. But if you just want the gradient for the leaf nodes, then that is the way we have to use to just use the gradient for this to save memory and some other stuff.
I have a very strong feeling that you are wrong. Yeah, so
I might be here.
so research it
Sure.
and update the result for
Sure.
everyone here,
Sure.
right?
Yeah.
But let me guess. So here is my guess.
Yeah.
So, however, you guys really need to understand what is autograd.
That is
You should understand autograd concept very, very well. So, and if not, for me, for example, there was a Stanford vision class, computer vision class, and what they did was they built a NumPy. They didn't use the PyTorch or TensorFlow. They just used the NumPy, right? And do those simple layer thing, right? So they have to develop forward and backward in your own class. So basically, you are building your own variable class, and it gives you understanding about what is the actually computation graph and what is the autograd. So, reading text, you might be ambiguous and you don't know you are understanding or not.
Yeah.
The best way is building simple one. So that way you can run.
Okay.
So you should master the concept of the autograd, and actually everyone should master this concept. So if Saroz explains his result on the Slack and you still don't understand, then you have to study it very carefully. So what is the autograd? Let's say you have a matrix multiplication, like y equals a multiplied by b, right? And what happens is, in the computation graph, you have a as an input, b as an output, and y as an output. And this node is a multiplication node. So what it will store is, let's say you want some kind of differentiation to get differentiation with respect to b. It will be like something like
partial derivative.
yeah, partial derivative, exactly. A, right? And so to get partial derivative in according to b, and to get partial derivative according to a, which is basically b. So you need to propagate. Let's say you somehow, this is the forward, but the backward is like you get this as an output, and you have to give so partial derivative of y according to the b as this number b, right? So this is basically b, and you have to give this one b y multiplied by this is a. And let's say you have one more node. Let's say this was a addition node. So there is an input like x, and there is a constant like c. So it was like b equals x plus c, some constant. Then at the end of the day, what you want to get is you want to get no, we don't want derivative over the x, but let's say this is some intermediate node. So to get this, you guys know the chain rule, right? So y multiplied by X. Yeah. So from here we can give this one this value, and using this value we can backpropagate this by y. So what it can do is we can calculate x. So my essence is, let's say you did a one pass and you want to do a backward. How you can get these values? The trick is you store them in your class. So in variable class, in variable in computation node. Yeah, in computation node, they store in each computation node, they store their inputs and outputs and use them to create a backward pass, right? That is for autograd thing. So you can actually build a simple autograd for fully connected layer using only NumPy. So if you would like to know how you can do it, that's a Stanford lecture homework. So you can try it. And let's say you have, so when in this PyTorch, the benefit of PyTorch is there is nothing like versus TensorFlow. So there is nothing like a graph building and session. So in TensorFlow, we had a separate two steps. We first build a graph, then we run the session, right, to actually do these things. And the confusion we had last time with the iSharas class was one of them was the misunderstanding of this concept, which is a little tricky, right? So that's why it was so difficult to get the size of the YS. So PyTorch is a more advanced one. It's difficult to say which one is better, but to give you an idea, if you are a company and would like to run a very huge model, then use the TensorFlow company. And if you are a graduate student with a single machine, PyTorch has a better productivity. It's easy to build and test ideas. It's more easier, right? So we will use PyTorch in our future. When we build some models, we will use a PyTorch. We learned the TensorFlow because the world model was on TensorFlow, right? It's probably the only reason why we studied TensorFlow. So in PyTorch, there is no separation of the graph building and the session. So when you do some operations like A plus B, it builds a computational graph. In it, every operation builds a computation graph. And what can be the problem of building a computation graph? I can think first thing, unnecessary computation graph is like a memory. So GPU memory is a very scarce, rare resource. And if you build lots of useless computation graph, it will keep the memory. And as I said, the variable is, there is the overhead used for many things. And let's look at these two comments on here, right? This one and this one. And think about the computation graph you build so far. And if we do not put this line, they will build a computation graph for this. right? So now the computation graph will have some kind of even loop inside this computation graph.
Did you say when we use with, does it make a computation graph or not?
No.
No.
So with no graph, now this line does not build a computation graph. So
it's just a mathematical calculation.
yeah, it's just a pure Python. We think it's a normal Python operation. These things, they even though they look like a normal Python operation, they are not actually normal Python operation. They are actually recording every computation graph for their interactions. And can anybody suggest why loop is a bad thing? Loop in the computation graph.
So it will keep flowing and keep going.
Yeah, keep going. Yeah, so we cannot backpropagate, right? It just keep going endlessly. So think of this computation graph. It uses W1, and W1 is from the W1 grad. However, W1 grad is from the W1, right? So you create infinite loop here. So and making a zero thing. So these things are what I think is the reason behind this no grad. However, I might be wrong. So it's your responsibility to study this very carefully and give us a very easy and compelling reason and make everybody understand the reason behind this. Okay?
So document here saying for the no grad, if you don't want to compute the gradient individually for that particular variable, then we keep for the no grad. So here in this example, W1, W2, we don't want to calculate the gradient in respect to W1 and W2. What is calculated against the output layer, we are just updating based on the learning rate and the previous weight. Because from this point, it is not backpropagating to another layer. So that may be the reason here. We don't need to calculate no gradient here.
So it's basically like not calculating individual gradients for.
So basically what happened backpropagation, we do W1 is equal to previous original W was minus alpha into gradient of your activation of your next layer to backpropagate this. So we are not backpropagating W1, W2 here to previous layer. So that's maybe the reason here. This is like last layer. Yeah. This is one.
Like you see.
Like first layer in the sense. From this point, you will not able to you don't want backpropagate your gradient. This is your pick.
Every time it runs, it's just calculating only for.
If you think about forward propagation and back propagation, so from backward you came to W1, W2. Now W1, W2, do you have any variable weight which need to be updated?
No.
So you don't need to calculate at this point.
Oh.
That's one of the possibility here.
Yeah, I read.
Pascal, here is my question. So, do you think this is unnecessary or actually not allowed? There is a difference between not necessary.
Yeah.
If something is not necessary but allowed, you can do it. It's just a waste of resource, right?
Yeah.
And if something is not allowed, then you cannot do it.
Yeah.
So do you think it's not necessary or not allowed here?
Here I think it is not necessary.
Okay.
So if we comment and uncomment, it should not throw error according to documentation. But I didn't run it.
Yeah. So, Saros?
Yeah.
I think it's not allowed, and Parod think not necessary. Do you know what I mean? So the no grad thing. If something is not necessary, you can do it, right?
Yeah.
Or you just don't have to. You
Right.
can do it, or you don't have to.
Right.
And if something is not allowed, you should not do it.
Yes.
Yeah. So I think I'm right.
Torch the flow to
Please give the who is right, right?
Okay.
After you study no plastic.
Okay.
Yeah, just
Modern
let
torch has
Pascal and me
no
and everybody know who is right.
at the same
Okay. So you are saying not allowed, right?
Yeah, I
The meaning
saying
of that
it's
is-
not allowed.
Yeah.
Pascal saying not necessary.
Okay. Sure. Yeah, so this is basically the training part for the neural network. So it's quite easy to PyTorch to like use PyTorch and build up calculating the gradient automatically. So it becomes little easier to use compared to TensorFlow. So should we run this code?
So I've done.
Yeah, this is just a training part I coded.
And is there any more part?
But this is just a simple, like we can do the prediction, right? But everything is random here. So
Okay. Okay. Please welcome Saros. And
our